All right, welcome to the second half of section 4.2 in your college algebra lectures. This is the second half of logarithmic functions. Logarithms have a lot that we had to talk about, and in the first half we talked about these first four topics, and so now we're going to discuss graphing logarithmic functions, finding the domain of a logarithmic function, and then two special types of logarithms known as the common and the natural logarithms. Okay? So if you remember how logarithms are defined in an inverse scenario. So the logarithm is the inverse of an exponential relationship. And if you remember how inverses work, inverses are found how? By switching the x's and the y's, right? And then solving for y, and in this case we just have to use the definition log base b of x. And so log base b of x is the inverse of b to the x power. And so when you switch x's and y's, what that means, if you take a look at the graph, we remember what the graph of b to the x looks like. This is for 3 to the x, where 3 is bigger than 1, so the graph goes up, goes through the point 0, 1. It has an asymptote at y equals 0, and it increases to the right. And so if you take the inverse of that, what does that mean? That means you switch all the x's and the y's. So instead of 0, 1, you have an x-intercept of 1, 0. Instead of an asymptote at y equals 0, you have an asymptote at x equals 0. Okay, and all your points get flipped over. You reflect above the y equals x line here. And so the blue, if the blue is your 3 to the x graph, then this red one is the log base 3 of x graph. Okay, and so that's kind of how you do it. Let's take a look at the properties. So if you remember again, for exponentials, the domain was all real numbers and the range was positives. So for a logarithmic function, the domain is positives and the range is all real numbers. Everything flips, all the x's and y's flipped, right? Instead of a y-intercept at 0, 1, you have an x-intercept at 1, 0. Okay, you're still going up to the right if b is bigger than 1. You're still going down to the right if b is less than 1, positive. And you have a x equals 0 vertical asymptote. Okay, so make sure you write those down. Pause the video at this point if you need to, because I went through those quickly, but you can read. And so make sure you make a note of those and see and compare how they reflect the opposite of the b to the x exponential functions. So the graph of log base b of x when b is bigger than 1 increases to the right. It starts to level off, okay? And when b is between 0 and 1, it decreases to the right, but it starts to level off, okay? And again, there's an asymptote here, right? There's an asymptote here at the line x equals 0. Preferably straight. All right, so let's graph the function f of x equals log base 4 of x plus 2. How are we going to do that? Well, what's the base graph look like? The base graph has an asymptote at x equals 0. It has an x-intercept of 1, 0, and it goes up to the right because b is bigger than 1. So that's what y equals log base 4 of x looks like. What does your graph look like? What does the plus 2 do? That shifts it to the left 2. Okay, so how's our graph going to look? Once again, we're going to have an asymptote, but the asymptote shifts left 2. So instead of x equals 0, what do you get? You get an asymptote at x equals negative 2. Okay, label it. You had an x-intercept at 1, 0. That shifts back 2, and so now you have an x-intercept at negative 1, 0. And then the graph, of course, goes up and levels off. Don't worry about where you cross the y-axis right now. Okay, and that is the graph of f of x. So that's how you do it. Simple shifting, same stuff. You just have to know the base graphs and those base graphs again are given here. Okay? Alrighty. So now let's talk about the domain. The domain of a logarithm function, if you remember properly, your domain is 0 to infinity, right? That's the domain for y equals log base b of x. Well, what if you don't just have an x? What if you have other stuff? Well, then you need that other stuff, x minus 5, you need it to be positive. X minus 5 needs to be greater than 0, not greater than or equal to, but greater than 0. And so what you do is you set whatever's inside the domain here, inside the log, you set it greater than 0, and then you solve. You get x greater than 5 in this case, and so that tells me that the domain of this function for f of x, the domain is 5 to infinity. Okay? So, if you want to find the logarithm domain, the domain of a logarithm function, you simply take the stuff inside the logarithm and you set it greater than 0 and solve. And that is your answer. That's all you do. Okay, kind of like the square root function, except you don't want greater than or equal to, you just want greater than. So pause the video and you guys try example number 2. Okay, so what's inside your logarithm? 2 minus 3x, so take 2 minus 3x, set it greater than 0. When you subtract 2 from both sides, you get negative 3x is greater than negative 2, but then if I divide by negative 3, that switches the inequality sign because it also switches all of the other signs, and so you get x less than 2/3. So our domain in this case is negative infinity to 2/3, not including the 2/3. And again, that's because if you plug in negative numbers here, right, negative times negative is positive, and that'll get you a positive thing inside there. So you just have to trust yourself. If you do the algebra properly, that's going to be your answer for the domain, whether it's positive numbers, negative numbers, whatever. Okay? All right. So now, there are 2 special types of logarithms. One is called the common logarithm, or common log. Okay, this is not when 2 logs live together for a long time and then they get each other's stuff. This is common logarithm, which means we're using the base of 10. Why is that thought of as common? Because we live in base 10, right? Our number system is base 10, and so that's a very common thing. And so on your calculator, you'll see a button for log with no base at all. That means base 10. Some of the newer calculators have a place where you can input the base itself. That's totally different. But if you're using an old calculator or scientific calculator, you just have log. If there's no base written, it's base 10. Now, the log base 10 properties are the same as the general properties for logarithm because 10 is just a regular base. So don't let that confuse you. Same rules. All right. Let's see an application of how log base 10 can be applied. Here's a function. F of x is equal to 29 plus 48.8 log x plus 1, no base, so that's base 10. Okay? X represents a boy's age from 5 to 15, and f of x is the percentage of his adult height that he's going to reach. So theoretically, when a boy is 5 years old, that's the percentage of the height that they're going to be. It's not perfect, but it is a model. And so we want to approximate what percentage of a boy's adult height has he attained by age 10 by using this formula. So what are we going to do? We're going to plug 10 in for x. Okay, so how does that look? Plug 10 in for x, you get 29 plus 48.8 log of 10 plus 1. 10 plus 1 is 11, so you get 29 plus 48.8 log of 11. And if you plug that in your calculator, you get approximately 80. 80%. Remember that f was given as a percentage, so you don't have to change from a decimal to a percentage. This is a percentage in the problem. Okay, and so what that means simply is that a 10-year-old boy has attained approximately 80% of his adult height, again, on average. Okay, so what about the natural logarithm function? The natural logarithm function is sometimes written log base e of x, but for shorthand, we can express that as ln of x. This is not an I, this is L. So this is not in, this is the natural log, ln of x, okay? So ln of x is fine, log base e of x is fine, but not ln base e of x. That doesn't make any sense. Either you use shorthand or you write the base, but don't combine them, okay? So just like the common logarithm, all the natural logarithm properties match up with the general properties for logarithms because e is just a number. It's bigger than 1, so it follows the properties for log base b bigger than 1. So why don't you guys pause the video at this point and y'all try to solve or use your calculator to solve this problem here. Read the problem, understand what it's saying, plug in for x, use your calculator and solve. And we'll come back in a minute and get ready to do that together. Okay, so what are we doing here? X is the number of minutes, okay, in which the air temperature has been changing in an enclosed vehicle. So after 30 minutes, what are we going to do? We're going to find f of 30. And so that gives us 13.4 natural log of 30 minus 11.6. If you plug that into your calculator, I've already typed it in here, 13.4 times ln is over here, okay? 30, make sure you close the parentheses, minus 11.6. If you hit enter, you get 33.976. And so this is approximately 33.976. What's our units? Degrees. And so it's about 34 degrees, or the temperature climbs 34 degrees in the first 30 minutes, right? This is why you can't leave your pet in the car when you run into the store and stuff. Or your kid, obviously, but that's a whole nother thing. All right, so it gets hot in there fast. And that's what that model shows us, okay? So work through the problems, the second half of section 4.2. So take a look at that and let me know if you have any questions. Thanks.